So let's begin with the vocabulary. Of course, statistics itself, and we kind of talked about this the other day, it is about taking sample data to make inferences about an entire population. We use statistics to find out what's going on, to look at trends, to measure population. So the two differences here, parameter is a measure that describes the population, where instead we have a statistic, which is a measurement that describes the sample. And that's really how to remember it. Population, parameter, statistic, sample. So you'll always know which one you're dealing with. So we talked a little bit too about our data. We talked about quantitative, but I don't think we talked about categorical data the other day. Quantitative data consists when I have numbers that are meaningful. Your age, the number of credits you're taking, your height, your weight, your GPA, things like that. These are meaningful numbers. And they are quantitative, numerical data. The other type of data is categorical or qualitative. That means the same thing. So in this case here, it says gender, male or female, what's your favorite color, what's your favorite ice cream. The test here is if it's meaningful if I add things together and divide by the number of things to get a mean. How would I be able to add together chocolate, vanilla, and strawberry ice cream and divide by 3? That wouldn't make any sense, would it? So that just is the good trick to say, hey, that means it's got to be categorical or qualitative data. The other example up here are the numbers that are on professional athletes' uniforms. So if I added the numbers on uniforms and divided it by the number of uniforms, would that mean anything to us? How about our phone numbers? It's still a number. If I added up 5 of your phone numbers divided by 5, would that mean anything? No, even though it's numbers, it's still got to be categorical or qualitative because those are meaningless as far as being a number from 1 to 10 or other meaning to us. Okay, so that's your test. Always think, can I add them up and divide by the number to see if I get a meaningful number? Okay, quantitative data, there's 2 types. One is discrete and one is continuous. The example says the number of eggs a hen would lay. Yesterday or Monday, we all rolled dice, and that was discrete because we could literally count how many times we rolled the sum of 3. It couldn't be 2.5, it couldn't be 1.5. It's either 1, 2, 3, or all the way up to 12, right? So we would know if that's discrete data. Continuous data, on the other hand, we talked about being your height, your weight. In other words, you might weigh 131.245 pounds. There's something in between 120 and 121. So that would be the difference between discrete and continuous. So if I were talking about the number of touchdowns team makes, is that discrete or continuous? Discrete, because I can literally count them. They can't make 2.5 touchdowns, right? So that would be discrete. So here we go to the levels of measurement. Sometimes these get a little confusing. Nominal level, things that cannot be put in order. They would be meaningless to be put in order. Okay, that would be nominal. That would be nominal. And we usually think about that as being categorical. Ordinal level, so it's that it can be arranged in order, but the distance between them aren't necessarily meaningful. So in the Catholic religion, we have different seasons or different times in the church calendar. And of course, there's the season of Christmas, there's the season of Easter, there's the season of Lent. But we also have ordinary time. Not because it's ordinary in the sense of the vocabulary ordinary, but because it's an ordinal level of measurement. It's the first week in ordinary time, the second week of ordinary time. So that is a level of measurement. Interval measurement is when we're dealing with numbers here, and 0 doesn't really mean anything. For instance, here, the years, if I just said 2017 or 2001 or 1996, there's no real 0 for a year. Okay, there's no real meaningful 0 for the year. The thing that's different between that and ratio measurement is that 0 is meaningful. 0 is meaningful. I would have 0 students in my class. Okay, something like that where 0 has a meaning. It's not present. Here's the one here is that they give you is the price on college textbooks. Wouldn't it be nice if you did have a no cost? That'd be the best of all, right? I think that happens when you borrow it from somebody, right? Okay. Nominal categories only, ordinary categories with some order, interval, no natural 0 point, but ratio does have that natural 0 point. That's the difference between the levels of measurement. Okay, collecting data. We talked about this yesterday as well. I don't care if you don't get a good sample, if you don't collect good data, nothing we do to it will save it. It's just bad. Nothing you can do to it is going to save that data. The method used to collect it is got to be of high quality. And we're going to talk a lot about what's called a simple random sample. A simple random sample was if I put everybody's name in this class in a bowl, shook them up, and then you pulled the names out. And this is going to be a group. Then I'd pull more names. You would be a group. That's a simple random sample. Difference between the types of studies. There are two types, observational study and experiment. So the way to tell them apart is did we do anything to those subjects, whatever the subjects were, whoever they were. For instance, if I wanted to know, and I was taking a sample, and I wanted to know how many credits you're taking. Did I change anything about those credits you're taking? Did I do anything to those credits you're taking? That would be considered observational. I'm just taking a look at what is actually happening. If I wanted to go on and get your GPA, did I do anything to influence your GPA? No, I'm just going and getting the actual data that's there. However, if it's an experimental study, I've done something to change something, or we hope we've changed something. An example would be, we do this all the time in medicine. We'll have two groups. A lot of times it's a blind or a double-blind study. And one group will get a placebo, meaning a fake medication, that there's not any medication in it. And the other group will get the new drug, the new medication. And those two groups would then be watched to see if the medication effective. Did I do something? Yes. Experimental. Experimental. Okay, what I'm doing right now, really, I could put it as an experimental study because I'm recording as I'm teaching the class, and I'm going to be putting those videos up for my online class. There's already videos there, but I'm willing to see if this will also help them. So I can compare from one semester when I didn't put extra videos up to this semester where I am going to put those videos and post them for those who want to see them. Now, I don't have any control if they watch them or not, but I can see, if there were any difference. One time wouldn't be enough, so it would have to be a longitudinal study. Again, I'd have to do it several times to really see that I'm getting good data and a good feedback of the study. Okay? So the Pew Research Center surveyed 2,252 adults and found that 59% of them go online wirelessly. Observational or experimental? Observational, excellent. In the largest public health experiment ever conducted, 200,745 children were given the Salk vaccine, while another 201,229 children were given a placebo. Experimental. We did something. Okay? Simple random sample. The number of subjects, whatever that number needs to be, is selected in such a way that every possible sample of that size has the same chance of being selected. So if I wanted to do that here, and again, put your names in a hat, draw out, here's a group, here's a group, here's a group. That's a simple random sample because you had the same opportunity, the same chance of being within that same sample. So I could have one sample of 5, mix them all up, get another sample of 5. So I have every possible sample having the same chance. A random section is now I'm going to be talking about the individual that was chosen. Okay, so I could shake that up and just pull one person. Everybody in here has the same chance of being that one individual that was chosen. Okay. Systematic. This is where you're going to pick every 5th person, every 10th person, every 7th person, whatever that number happens to be. Systematic. We talked about that doing outside of the mall and seeing if that would be a good sample, right? We decided, nope, because we are influencing that sample by being where we want people to say yes, they wanted a new mall. Convenience sample. When's somebody going to answer a convenience sample? When it's convenient. And you know what? If it's something I don't care about, am I going to take the time to answer it? We are too busy in life, right? So if it's not something I feel passionate about, one way or the other, I'm not going to do that. I'm not going to answer that particular survey. It can come in the mail all it wants to, right? I feel also about that for evaluations at the end of courses. I get to see all the evaluations for every faculty member for every class they teach in my department. And I know that I need to take it with a grain of salt. What do I mean by that?
That student might not like that teacher, or they might really like that teacher, or they might be too busy and don't answer at all.
Exactly. And if you're a student who could care one way or the other about a particular class or a particular instructor, are you going to take the time? Probably not. If you had a really bad experience in your eyes, Are you probably going to go on? Yep, because you want me to know about it and you want them to know about it. In the same respect, if you have a fantastic experience in a class, probably want to go on, right? And tell them and let them know. So we have to look for patterns in those evaluations. One bad one, pff, oh well, right? But if I see that over multiple courses or multiple students in the same class, then that's a red flag. But do you see where you have to kind of weigh that out? Okay, good. A stratified sample. This is where we're going to subdivide the population. Many times it's men and women. Maybe it could be by age groups. Maybe it could be by towns in the state of Delaware. Seaford, Milford, Millsboro, Newark, Wilmington, Newcastle, etc. Those are all then subgroups of the state of Delaware. And then I would draw a sample from each of those subgroups. Okay? That being different. Hmm? They said their difference is women and men are my two subgroups. Okay? And then they picked randomly 3 out of the 4. Okay? So that's the key, is that when you're looking at stratified, I keep it with S being sample, so that keeps it, that's my way of remembering, stratified into groups and then samples from the groups. Stratified S, samples from the groups. Because the other one, the next one, is called a cluster sampling, where here they're picking particular precincts, but in the case that I just said, where we pick particular towns in the state of Delaware, Laurel and Woodbridge and Greenwood. I'm trying to go up from the north, go up from south to north to Dover to, I don't know all the towns in Delaware, to Middletown, to Newark, to Wilmington. And I put all those towns in a hat, and I pulled out 3 of those towns. Then I would use the entire town, everybody that lived in that town. That's cluster. Okay? So I'm taking the whole cluster of people. Stratified sample from the divided groups. Okay? We used this method when we had to do our student learning outcomes assessment measurements. Instead of getting all the students and putting your names in a hat for elementary algebra, instead we put all the section numbers in the hat. We drew out 3 section numbers and used every student's test from those 3 sections instead of putting everybody's name in there. Okay? Different ways that are acceptable ways to get your sample. Multi-stage is when you're going to use a combination of some of these. Could use a combination. So our methods of sampling, just to remind you, random, just randomly pull. Systematic is what? Every Kth person or every 5th person or 7th person or 12th person. Convenience? Yeah, I'm just going to ask, put it out there and see who responds. Stratified? Break them into groups and then what? Get the samples from each group. Cluster? Divide into clusters and take the whole group from the cluster, from that particular cluster. And of course, multi-stages combine more than one. Okay, types of studies. I know this is the boring part. Sorry. Because it's all the vocab. Cross-sectional study. This is going to happen when I'm trying to measure change over time. Cross-sectional study. Data observed and at one point in time. So I can look at, maybe we're trying to see where students have problems in a particular course. I'm going to look at where they are at week 4. Okay? Retrospective is when I'm going to go back from the past and examine records that are already there. I'm just examining records that are already there, that have already done. And then longitudinal is where I look to the forward, to the future. We do that a lot with cohorts. When you come into the college, you don't even know that we put you in a cohort, depending upon what year or what semester you began, and you are in that cohort. So if you came last fall, you would be in the 2017 5-1 cohort. And we have to pull data that we have to report to the federal government about students from that cohort. And it's put on the internet, on iPads. Design of experiments, randomization. Of course, that means we're going to put them in 2 different groups and just randomly put them there. Replication, I'm going to use a sample that's large enough, and I'm going to be repeating things. And it's still based on randomness. Blinding and double blinding. So that would go back to medication that's brand new. To give you an example, this side is going to get a placebo. This side or this group is going to get the real thing. You do not know whether you got the placebo or the real thing. That's a blind experiment. Now, sometimes those people who are conducting those experiments will try to look for positives. So a double-blind experiment is when that me who is conducting the experiment, I don't know which group gets the placebo and which gets the real deal. Double-blind. Okay, so you're not, you take out bias by doing that. So this is a problem that occurs in experiments. It's called a confounding variable. When you can't control things that may be giving you an effect on whatever you're testing. For instance, we are doing something new at the college called supplemental instruction. We call it SI, and we're just in piloting stages. So we are comparing groups who have SI, comparing them to groups of students who don't have the SI experience. So that is an experiment, aren't I? I'm doing something to a group. Okay? Now it can't be a blind because you know when you are in an SI section. So it can't be blind, and it certainly can't be double blind because we have to arrange everything, right? But in that, we have what could be, we call them lurking variables or confounding variables. What if a section that did not have the SI has a brand new faculty member with almost no experience? You know, 19 years, you learn stuff. But the SI person has a faculty member that's had 20 years of experience. That's a confounding variable. That's something that I can't control, and it's just there. Okay? the other thing that I can't control is maybe students and how they registered for classes. Maybe you are a morning person and there aren't any seats left in the morning classes. Or maybe you're not a morning person and the only seats left are in the 8:30 in the morning class. So those are confounding variables that we can't um, separate out from what we're actually doing to the groups. Confounding or lurking, okay? Very difficult to plan an experiment that won't have any. So some of the ways we like to control it is completely randomize the experimental design. We do a randomized block design, matched pairs design, and I'm not going to test you on all these, but I just want you to know what different designs there are, and very rigorously controlled design. So we try to do this with our SI sections. Very, very difficult because I can't be there to see what goes on in every section, obviously. But we try to keep them as close to being the same as possible. So we want to compare the groups. I even tried to have it so that a faculty member that had two sections, one would be with SI and one would be without SI. See how I'm taking away part of that confounding or lurking variable? That would be considered rigorously controlled. Okay, and just a summary here. For when you're designing experiments, randomizing, doing replication, repeating over and over again, and controlling the effects of those confounding variables. There are errors that can be made. A sampling error, and the sampling error is the difference between what you expect from the population and what you get from your sample. The non-sampling error, it's where the actual sample data is incorrectly collected. Could be incorrectly analyzed, it could be incorrectly recorded, something of that nature. And then a non-random random sampling error results when I didn't do something random. I said it was random, but it's not random, such as a convenient sample or voluntary response. And that's one of the things that we can't control with the SI is because we can't control which students are going into which sections, and we don't tell you which sections are SI. See, so that's not something that we can control. Okay. See if I can get my recorder up here. Okay, so we're going to move right on into section 2.2. We're going to use different ways of summarizing data, especially when there's large and large and large amounts of data. For instance, if I wanted to know, we have probably somewhere between 2,500 and 2,700 students that we service in the math physics department every semester. So there's quite a few of you. With that, if I wanted to know some attribute about you, I don't know, maybe I was going to put you in groups for or collect data on you about GPA from high school and compare that to your GPA at the college to see if there would be some correlation. That would be an interesting thing. I'm sure we've done it somewhere. But there's so much data on 2,700 of you, I would need to put it in something to organize it and summarize the data. Okay? And we do a frequency distribution very, very often. So it's a frequency data, and it will show the data by classes, meaning intervals or widths, and then how many frequency of each. So maybe I would be looking at a GPA from 1.9 to 2.1. How many of you had a GPA in that range? See, so I can group that. I can see that very quickly rather than just have a long list of GPAs. So here's one example. IQ scores of low lead group of individuals. Lower class limits are the smallest numbers. So here obviously it would be 50, 70, 90. And you're seeing that whatever that IQ is, I'm grouping people that have an IQ from 50 to 69, then from 70 to 89. So my lower class has the same difference or same change, 50, 70, 90, 110, 130. The same thing's going to happen on the upper class limit. Once I have that upper class limit, 69, I can just add 20 to each one. That's called the upper class limit. They should be the same for each interval. In other words, I wouldn't want this to be 50 to 69 and this one to be 70 to 79, because then this would have to be 80. They have to have the same width each time. If not, I can sway my data because I can make it look different because I'm changing that width. So then there's something called class boundaries. And the class boundaries, what you do is you look between 69 and 70. Well, obviously between 69 and 70, there's one in between that. You can add them, divide by 2, or just know, hey, there's a half in between there. So from my lower, I'm going to subtract the half all the way down. Those are called my boundaries. My boundaries. Class midpoints. Well, we had already talked earlier about finding a mean. I can add 5 things up, divide by 5, and I can get a mean, which we also think of as the average. Once you get data, which is no longer raw data, I have to do something different to be able to calculate all the things that I want statistically. All I know when I look at this data is that there are 2 individuals who have an IQ somewhere between 50 and 69. I don't know if one has a 50 and one has a 69. I don't know if one has a 62. I have one has a 59. I have no idea. I've lost the raw data. I couldn't tell you, these 33 people, what their IQ was. I just know that 33 of them have an IQ between 70 and 89. That's all I know. So when we're getting ready to do calculations, we're going to find what's called the class midpoint. Literally, add those 2 and divide by 2. You're getting right in the center. That's all you do. Our class widths, what did you count by? 50, 70, 90. You're counting by 20s. That's just our class width. The reasons there, of course, we talked about large data. If I take large data, summarize it, I can look at it and analyze it much easier. And we then have a basis for constructing really important graphs that we can see. So this goes in how you're going to construct a frequency distribution, and we're going to do some examples. Determine the classes, and the classes are going to be determined by the range of the data that you have. So if you have IQ scores usually don't run any lower than, say, 50 and any higher than, say, well, we have a few individuals, I guess, at 140, 160, say. So I'm going to look at the range and say, hey, is that too many to get in 5 classes? Maybe I need 6 classes. And determine that, and then we're going to look at the maximum and minimum, divide by the number of classes we want, so we have an approximate class width. Okay? Choose your lower limit, your class width, make your chart, and then you'll start putting a tally mark in each of those particular widths so we know the frequency. Relative frequency distribution. And relative frequency distribution is nothing more than the percentage of frequency. How often does it occur? So the percentage, of course, we're going to take the frequency, divide by all of them. That gives us our percentage, and we multiply by 100 to get percent. So that would be the idea of a relative frequency. So what does all that mean? First, we would total this column. Whoops. Everybody can get your calculators out. Let's total that column. I think we get 78. 78. So we have a total here of 78. How many of the first one? 2. So I'm going to take 2 divided by 78. Do you get 0.026? That's how they got to 2.6. Relative frequency. Okay? Cumulative frequencies. We had 2. Cumulative means you're going to add as you go. There's 33 in the next class, so 2 plus 33 is 35. 35 plus 35 is 70, and so forth. That's cumulative frequencies. So one of the things that we want to do when we look at a frequency distribution, and that's really what we did when we summed our dice and we came up and we put the numbers on, we were looking at a frequency distribution. We want to know if it is a normal distribution. Well, what is a normal distribution? If it approximates what we know to be the normal curve. It starts low, it increases, and then goes back to being low. It is approximately symmetrical. I know my drawing's not very good, but that's meant to be pretty symmetrical, okay? In other words, I could put a mirror right here and decide would fall on each other. It should be pretty symmetrical. Now, are you going to get absolutely perfect ones? Not usually, because we're doing samples, or we may be doing sample of sample means. But you'll be able to see if that general shape, just like we did with the dice and the sums. It wasn't perfect, but had we keep on going and going and going, it would have gotten more perfect with more samples. If we have gaps, it means there's no data. Or sometimes it's from 2 different populations. So for instance, trying to think of one that would be, I was going to say the weights of dogs and the weights of cats, but there's some dogs that are so teeny tiny, right? I saw one the other day, I think that dog must only weigh 2 pounds, honestly. But I'm trying to think of 2 different populations that you might have where there would be something distinct, that you would see them apart and you'd have gaps. So let's take a look at the example on the next page with the frequency distribution. It is weights of pennies and grams. Why is this true? Pennies made before, did you guys know that? Pennies made before 19 knew it? Before 1983 are 95% copper and they are only 5% zinc. Well, if, as you know, what has happened to the price of copper? So, what does that really mean? A penny that's 1983 or earlier is worth more than a penny. Definitely. So it is. And pennies made after 1983 are, wow, 2.5% copper and 97.5% zinc. What a difference, yes? It's because of the cost of copper and the value of copper. So if you have a lot of those, you know they're worth a lot more, correct? They have a lot of the old wheat ones. Remember the wheat pennies, or am I just old? They were wheat pennies. So look at this frequency table. Pennies for the weights would be 2.4 to 2.49, 18 of them, 2.5 to 19. Look right here, nothing. There are none. And then you get to this weight, okay? Because again, two different populations, so to speak, of pennies because we know what the copper was, okay? That is all of 2.2.